Hey, I just wanted to quickly plug that if you guys want any tutoring, some new slots have opened. If you look in the description, there's a link to my physics and maths tutor profile in which I do tutoring on there. Hello, and welcome back to another episode of the A-Level Cookbook. Today we're going to be doing the OCR A-Level Chemistry A, Paper 3 from June 2018. This is the exact paper that I did as well. So I did AQA A-Level Biology, I did OCR A Chemistry, and I also did OCR Maths, and I also did OCR B Physics as well. So this will be fun. So this question refers to the elements in the first three periods, H they are in the periodic table. Select an element from the first three periods that fits these descriptions. So it forms a 1- ion with the same electron configuration as helium. So if it's helium and with an electron configuration, if we have a look, helium is going to be 1s. Helium's electron configuration is 1s2, and it's forming a 1- ion. So whatever it was originally was 1s1, which is going to just be hydrogen. So that's that. Then it says the element with the highest first ionization energy. So the ionization energy, remember, is the amount of energy you need to put in to remove an electron from the outermost shell. So whatever it is has an electron whizzing around here in its nucleus, and it's being pulled the most here. So we want something that doesn't have too much shielding, the minimum number of shells, but as well as that, the strongest possible nuclear charge. So it's going to be helium, because helium has 2 protons in air, and it has 2 electrons out here, but those electrons are closer and it has a smaller atomic radius, whereas hydrogen only has one proton, 1 electron. So the attraction is stronger here. So that means it's got to be helium. Then it says the element in period 3, which has these successive ionization energies shown below. So from here to here, there's about a 700 gap. From here to here, it's about 6,000. So we've removed 2 of them, and now we've gotten into a new shell here, most likely. So that means it's in period 3, and it's probably going to have 2 in its outermost electrons. So it's going to be in the S block, because it's only got 2 electrons in its outer shell that we've nabbed. Period 3, so period 1, 2, 3. So it's got to be magnesium. There you go, wherever that's gone. Magnesium. Then it says the element which forms a compound with fluorine that has an octahedral molecule. So octahedral is 6 bonding pairs, 0 lone pairs, SF6, so it's got to be sulfur. Now it says an element which reacts with water to form an acidic solution. So some mysterious thing, you add it to water, it makes acid. It's going to be either chlorine or fluorine, either one of those two, Cl2, because if you react them, remember you end up getting Cl2 plus H2O makes HCl and HClO, the disproportionation reaction, the funky one there. The element X, which forms a compound with hydrogen, XH3, with the molar mass of this, right? So if it's H3, then the molar mass, well, if you take the 3 H's off, it's just going to be 31. So whichever one has a mass of 31, which is phosphorus on the periodic table. An element which forms a compound with hydrogen in which the element has an oxidation number of -4. So whatever this mysterious thing is has a -4 oxidation state, it's going to be H4, right? So it's going to be something that can form 4 bonds of the, H's here. So it's going to be in group 4, carbon, CH4. And then the element which has a density of this at room temperature and pressure. So if we have a look, it's 1.33 times 10 to the -3 grams per centimeter cubed, right? These are all measured in grams per mole. So we need to try and figure out if we can get there. So if it has a density of grams per centimeter cubed, then 1 centimeter cubed would give you 1.33 times 10 to the -3 grams. That's how much it would weigh, right? Now, we need to figure out real quick what 1 centimeter cubed is in moles. So moles equals volume over 24,000, right? So if we have 1 centimeter cubed, it's going to be 1 over 24,000 moles. That weighs this much, right? These are all grams per mole in the periodic table. Grams per mole means that 1 mole of this weighs this much. So here, if we have 1 over 24000 moles, and that weighs 1.33 times 10 to the -3, then that means that 1 mole of this would weigh 1.33 times 10 to the -3 times 24,000, which is 32, right? So this MR is 32. It's got to be gaseous because, it's a volume and a density thing here. So it can't really be sulfur because that's a solid. However, if I half it, you end up getting 16. So it's oxygen or O2. There you go. This table shows some properties of period 3 chlorides. Explain the properties shown in terms of bonding and structure. This should be 3 marks if you sort of do it systematically and properly and not just yap memorized answers. So here, NaCl, it's terrible at conducting electricity when it's solid, but it's good when it's a liquid. And its melting point is really high. MgCl2, same things here. Here, SiCl4, it's terrible at conducting electricity both as a solid and a liquid, and it has a low melting point. PCl3, similar thing, and then SCl2, same thing here. So we need to compare them in terms of their bonding and structure. So if we have a look at NaCl and MgCl2, right, together, because they share similar properties, MgCl2, they have giant ionic lattices, right? So then we need to explain their properties. So they'll have a high melting point because we're breaking those ionic bonds here, which require a lot of energy to overcome. So they have a high melting point because ionic bonds stronger and require more energy to overcome. And then why can they can only conduct as a liquid as the ions are free to move. They cannot as a solid. You cannot say that they are, transferring electrons. They're not. They're actually carrying the charges themselves. So there's that. Now, if we have a look at the SiCl4, PCl3, and SCl2, right? In all three of these, SiCl4, it's covalent. This is simple covalent, and that's simple covalent. Don't get thrown off by the Si bit. SiO2 is your giant, macromolecular giant covalent, right? Here, these are all simple molecular compounds, and the fact that they've all got low boiling points or melting points, also gives it away. So then here, all three of these, so SiCl4, PCl3, SCl2, they are simple molecular, and when you say lattices, it's just because they're solid. So simple molecular lattices, they have a lower melting point because they have London forces, which are weaker than ionic, and they require less energy, to overcome. And then in that case as well, they cannot conduct electricity at all because they have no mobile charge carriers, e.g. delocalized electrons or ions. And there you go. Step by step in, you'll be chilling. So this question looks at the reactions of hydrogen peroxide and cobalt ions, and this hydrogen peroxide decomposes as shown. The reaction is catalyzed by manganese 4 oxide. The student investigates the decomposition of hydrogen peroxide as outlined below. So what they do is they add 50 centimeters cubed of this to a conical flask, they add a small spatula of MnO2, and then quickly connect the flask to a gas syringe, and then they measure the volume every 200 seconds. Process the results as outlined below. On page 5, plot a graph of this against time, so the volume against time, and then use a graph to find the rate of reaction at t equals 500 seconds. So I'm just going to skip plotting it just for the sake of time, so 1 sec. So what you end up getting is you get like a nice curve like this, right? And ignore the tangent bit, that's from the mark scheme. You should get a smooth curved line best fit, and you should try and use at least half of the space that's there, right? Now here, they've told you to do volume against time as well. So you can't just do like 1/t, although it's tempting. They want you to do the volume against time. Then it says, use your graph to find the rate of reaction at 500 seconds. A rate is a change in something over the change in something, like a change in concentration, right? So here we have a volume and we have time. The gradient of this graph is going to be the change in y and the change in over the change in x, which is the change in the volume over the change in time, which is a rate. So what you do is can you see how so another word, for gradient is steepness. The steepness is changing, so the gradient is changing. If the gradient is changing, it means the rate is also changing, which is why they've pointed out you need to do it at 500 seconds. So what you do is you find where the 500 seconds point is, and you draw a tangent, because that tangent will have the same gradient at that exact point. Because if you zoom in on the curve, it will look like this. If you zoom in really far, it'll be kind of really close to being straight lined, and that's where that tangent is, where it can work out the gradient. So what you'll do is you'll pick 2 points, and you'll do y2 minus y1 over x2 minus x1, and that will give you the rate. So in this example here, they've picked 50 minus 11. So you do 50 minus 11, all divided by the second x coordinate minus the first, which is 920 minus 0. And if you do that, you get 0.042. And that's how you do those. So now the student allows this reaction to proceed until no more gas is made, and then the volume of the O2 is now 55 centimeters cubed at room temperature. Calculate the initial concentration and give your answer to 2 significant figures. If you're going to do any moly stuff, go and remind yourself what the proportions of each of them are. The ratio of this oxygen to the H2O2 is 1 to 2, or 2 to 1, 2 to 1, H2O2 and O2. They've told you that the volume of the gas is this, and it's at room temperature and pressure, so the moles of O2 is going to equal its volume over 24,000. So 24,000, if we do that, we end up getting 2.29 times 10 to the minus 3 moles of the O2. So from the equation, we now know the moles of the H2O2 is going to equal 2 times this, which is going to be 4.58 times 10 to the minus 3 moles. They want you to work out the initial concentration of the H2O2. The H2O2 concentration is going to be the moles that we just had, 4.58 times 10 to the minus 3, divided by whatever volume it was. Do we have its volume anywhere? Where is it? There you go, 50 centimeters cubed. So it would be 50 divided by 1,000, and you end up getting 0.092. You should stick to the significant figures they've told you there, and there you go. Now it says hydrogen peroxide can act as an oxidizing agent or a reducing agent. Some standard electrode potentials are shown here. So then it says use this information to write an equation for the reaction in which hydrogen peroxide is acting as a reducing agent. So this means that this is going to be a reducing agent, which means it itself is oxidized. So we're going to find whichever ones have H2O2 in, that's being oxidized. H2O2 being oxidized means the electrons are on the other side. So this one is what we are choosing as it's oxidized. It itself is getting oxidized. Something else has to be reduced. And if we're running a cell that does that, then it's got to be more positive than this, because that's what they're telling you is running. So here, what are the options? So it's obviously not going to be that one, because we're going to be just messing around with itself. That's not it. So this whole thing is out. Then here, we either have this or this. Well, this is going to be 0.68. We need something that's more positive. So that one's going to be more positive. That one's the one that's reduced. So then what you do is you would times this by 5, and then you would times that by 2, and then you would combine them, and then cancel out all your H pluses and your O's and your thises and your that's. Eventually, you end up with, just for the sake of time, I'll just skip through that, 2MnO4 minus plus 5H2O2 plus 6H plus gives you 2Mn2 plus 8H2O plus 5O2. That's how you do it. There you go. Again, just be careful with the question, not to just jump to looking at the numbers when they tell you what's doing what already. They've told you that this has to be oxidized no matter what. So then everything else you pick has to be reduced, which fits the bill here. Cobalt 2 forms complex ions with water ligands, and with chloride ligands. With water ligands, cobalt 2 forms a pink octahedral complex, which is this. With chloride ligands, cobalt 2 forms a blue tetrahedral complex ion. A student dissolves cobalt 2 sulfate in water in a boiling tube and a pink solution forms. So in experiment 1, what they do is they put this boiling tube at a water bath at 100 degrees, they add concentrated HCl, and then the color changes from pink to blue, and they do this dropwise. In experiment 2, what they do is they put it in this boiling tube from experiment 1 in a water bath, and then the color changes from blue to pink. It says write the equilibrium equation for the reaction that takes place when the color of the solution changes. So immediately write down what you know. So we've got CO, H2O, 6, 2 plus, and we're adding Cls, and it's told you when the ligands are swapped, it becomes, different colors. So in this case, we're going to be adding Cl minus, and it's tetrahedral, meaning you can only fit 4 anyway, and you should remember that Cl you can only fit 4 around anyway. So it's going to be ClCl4, 2 minus, plus the waters that's been booted off, so that's going to be this. So we're adding 4 Cls there. That's it, done. So it's equilibrium as well, so it's reversible. Then it says, explain these observations and predict whether the formation of the blue color is endothermic or exothermic. So here, this is pink, and this is blue, right? So if we have a look, they've done this boiling tube thing here, and it's gone blue. So it started off blue, they've then cooled it down, and then it becomes pink. So what they've done then is if they're cooling it down, they are decreasing the temperature, aren't they? So a decrease in temperature means that this equilibrium would counteract the change by shifting to the side that increase temperature. Right? It's always helpful to point that out because then it makes sense. Here, you can see that it's gone from blue to pink, right? Which means it does this by shifting to the left. Therefore, the forward reaction to become blue, because remember that's blue, is endothermic. There you go. Because if it's shifting this way to increase the temperature, that has to be exothermic. So it's always helpful to spell it out like that step by step, and then you kind of don't get confused and lost. I think that's helpful. And it also means you secure the bag in every single mark because you're saying, the equilibrium shifts to counteract the change, but counteracting the change isn't usually enough to say a mark, to be honest. But by saying by default what the change is that it's counteracting, and you can say it does this by either reacting or doing this or whatever, you've knuckled it down and always finessed it like that. There you go. So this question's about ethane dioic acid and ethane dioate ions. The ethane dioate ion shown below connect as a bidentate ligand. Fe3 plus forms a complex ion with 3 ethane dioate ions, and the complex ion has 2 optical isomers. Draw the 3D shapes of these, and then in your diagram show the structure of the ethane dioate ligands and any overall charge. So what we've got to do is we've got to draw our central metal ion and our wedges and our dotted lines and dashes and all that jazz, right? So let's do this real quick here, right? Now it's an ethane dioate ion. We need to remember that all ligands work by forming dative covalent bonds. So it has to have lone pairs of electrons. Those lone pairs are here. That's why these are O minuses, because they have an extra electron that's ready to give. So when drawing these, what I always recommend is you draw it lone pair by lone pair. So draw the lone pairs here and then connect them like that. So here, 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 double bond O, and then the next part, so lone pair, here, 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 double bond O, lone pair, here, 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 double bond O, and then we need to square this whole thing off. It's Fe3 plus, right? But remember that we've got 3 bidentate ligands, and they're all 2 minuses, right? So it's going to be 3 minus 6, so it's going to be 3 minus overall, and then the other optical isomer that we have to draw is the mirror image of this whole thing. So we do that. Same thing. Start off by just drawing those dotted lines and dashed wedges and all that jazz, and then just mirror it. So lone pair, O, here, 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 double bond O, and then lone pair, oxygen, lone pair, oxygen, here, 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 double bond O, lone pair here, lone pair here, oxygen, here, 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 double bond O. And that way you don't screw up and fumble it, and then the 3 minus is there. Done. So ethane dioic acid is present in rhubarb leaves. The student does a redox titration using aqueous carium sulfate, CeSO4, to determine the percentage by mass of ethane dioic acid in rhubarb leaves. In this titration, Ce4 plus ions oxidize ethane dioic acid in hot acidic conditions. 2 Ce4 plus COH2, so ethane dioic acid, makes 2 Ce3 plus, 2 CO2, and 2H plus. These have a yellow color, whereas Ce3 plus is colorless. What they do is they get 82.68 grams of rhubarb leaves and extract the ethane dioic acid from the leaves. They then add it to dilute sulfuric acid. They get a colorless solution, which is made up to this in distilled water, and then they heat 25 centimeters cubed of this and then titrate it with this much CaSO4, and then they repeat this titration to get concordant results. Fine. So then it says, this titration is self-indicating. The student does not need to add an indicator. What color change would you observe at the end point? This Ce4 plus is reacting with the COH, right? So you would have yellow stuff in the burette, right? And then it would be colorless as you're doing the reaction as this is made. However, we're talking about the end point. The end point is when you just overshoot and you get that color change. So in a perfect reaction, it would end at a colorless point, but obviously we don't know if it's finished. So what you do is you add a bit more, and then you'll have this that's unreacted, so it becomes yellow. So it's actually here colorless to yellow, right? Because in the same sense, for example, if you use phenolphthalein, that goes pink when you have an alkaline solution. What we'll do is we'll keep adding alkali and it'll stay colorless. And the moment you add that one drop and it becomes pink, you know the reaction's done, the titration's finished, right? It's the same thing here. So although yes, in the burette it's yellow, the reaction becomes colorless, but the moment you then become yellow again, that means you've overshot and you've got some extra 4E pluses, which means you've finished the reaction there. So now here, it says calculate the percentage by mass of ethane dioic acid in the rhubarb leaves. Give you an answer in appropriate number of significant figures. Usually just follow what the question's given you. So here they've given us 3, we'll stick to 3. Now, in these styles of questions, you need to just follow the story and make sense of what's happening, because that is a huge paragraph, a bunch of paragraphs and texts. You're just going to be all over the place, right? What they've done, step by step, figure out what's going on. So they do a redox titration with this and whatever, right? So what they do is the student weighs these rhubarb leaves. So we have 82.68 grams of these leaves. And what they do is they extract the ethane dioic acid. So what they do is they get the ethane dioic acid. So what they'll do is I'm just going to write the COOH2 here. They get this and they add it to dilute sulfuric acid, and there's 250 centimeters cubed. So in this, really, we have 250 centimeters cubed of this ethane dioic acid that will have come from the leaves, right? Then what did they do? They then took 25 centimeters cubed of this stuff, remember, of this COOH2. The acid bit is just an extra bit, right? And also, as well as that, the heating isn't relevant. I just want to know what's reacting with what. Otherwise, I can't do this. Any type of moly titration equation, need to know molar ratios and where everything's coming from. So we're getting this, and then what we are doing is we're titrating it. So we're reacting this with CeSO4 from the burette, and we know its concentration is 0.05, right? But we don't know its volume. However, this is in the burette, and we have our titrations here. So the volume is just going to be our mean titer of this stuff. So the mean titer is the ones that are concordant. So we pick the ones that are concordant. We need to work out the titers, so they're not giving us that, which is really annoying. So if I just quickly work those out, you would do the final minus the initial, so you'd end up getting this 23.15. So concordant is within 0.1 of each other, so it's these two we want. So our mean titer is going to be 23.25 plus 23.15. Sorry, that's supposed to be a 3. My handwriting is horrendous. I promise it's better than this, I swear. Divided by 2, because my tablet is just tweaking. That's why I have to write really weirdly. But anyway, yeah, that's going to give you a mean titer of 23.2 centimeters cubed. So now we know the concentration of volume of this stuff, which reacted with the COOH, which all came from here eventually, which is all in the leaves. Now I can find out how much of this is going to be the acid. Easy peasy. So what I do is I'll work out the moles of the Ce4 plus that reacted with the COOH, right? That's going to be its concentration times the volume, which is going to be concentration is 0.05 times the volume, which we just worked out, 23.2 over 1,000. If you end up doing that, we get 1.16 times 10 to the minus 3 moles. Then we'll work out the moles of the COOH2 in 25 centimeters cubed. Write that down. Force yourself to. You don't have a choice. Here, we can see that they react in a 2-to-1 ratio. So that means we're going to have to halve our answer here. So it's going to be a half of the answer, which is going to be 5.8 times 10 to the minus 4 moles. Now we need to work backwards because we want to eventually find out how much is in the leaves here, which is from this 250 centimeter cubed. So we need to now work out the moles of the COOH2 in 250 centimeters cubed. So you would do your answer times 250 over 25 or 10, and you end up getting 5.8 times 10 to the minus 3 moles. Now the question wants the percentage by mass of ethane dioic acid in leaves. All of the moles of the acid in here would have come from those leaves, so then we can just work out the mass of the COOH2 by doing moles times the MR, which is going to be 5.8 times 10 to the minus 3 times the MR of it, which is going to be 90. And you'll end up getting 0.522 grams. Percentage by mass is just going to be 0.522 divided by the mass of the rhubarbs, which is 82.68 times 100. If you do that, you end up getting 0.631% to 3 significant figures, because that's what they gave us in the question. There you go. So this question is about 2 compounds used in medicine. Cisplatin is a complex of platinum, which is used in cancer treatment. What's the oxidation number of platinum in cisplatin? So here, it's got 2 Cl minuses. The NH3s are neutral, but they don't have an overall charge. So minus 2, it's got to be plus 2, plus 2. There you go. Now it says cisplatin is prepared in a ligand substitution reaction which takes place in multiple steps. The equation for the final step forming this is shown below. So you've got PtCl3, NH3, and it's a minus, and then we add an NH3, and what happens is you end up getting PtCl2, NH3, 2, and then you also get a Cl minus there. So in the box below, outline the mechanism for the formation of cisplatin from PtCl3 minus and use curly arrows and lone pairs where appropriate. So, juicy, isn't it, right? But don't get thrown off. All you've got to do is just draw what they've told you straight away. Don't get thrown off by the fact this is an unfamiliar mechanism. Just start with what you know. We know that we're going to be reacting PtCl3 with an NH on it. So draw your dotted lines and your dashes, wedges, whatever, right? So we got Cl, 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 NH3, and the whole thing is a minus, and they've added NH3. For some reason, this NH3 is going to be bonding with here, right? That's how it reacts. If it's bonding with this, that's why it ends up here. So can you compare side to side? PT's only got one NH3, but now it has two, and it has one less Cl. Whenever you're drawing mechanisms with curly arrows, if you're showing a bond breaking, you have to show where the arrows go. You can't just magically make it disappear. The whole point of mechanisms is showing bond making, bond breaking, because of electrons going this way or that way, right? So here, if it's going to make a bond with a PT, the PT is not going to give electrons to this. This is going to give electrons to the PT. The reason being is because it has that lovely lone pair, because it forms a dative covalent bond. Problem is now we have too many things around the PT, and also here there aren't, 3 Cls and 2 NH3s. So we booted off one of the Cls. So think about it logically, right? Rather than just memorizing like an arrow and thinking, oh, it must be this way or whatever, or this, right? If I drew an arrow from the Cl to this, we're adding electrons into here. So this PT is actually going to have more electrons and it would be, negatively charged. Here you can see there's a Cl minus. So here it must have taken the electrons from this. So what happens is the bond breaks by doing this, like that. And that's what you end up getting, because then this is heterolytic fission. It will take both the electrons from this, and it will end up being Cl minus, which has a lone pair, which makes sense because these all have lone pairs, right? And they all have dative covalent bonds. And we've now stuck this NH3 on here as well, like that. That's it. There you go. Paracetamol is a solid organic compound used in tablets as a painkiller. Name the functional groups in this. So we have a benzene with an OH, so it's phenol. And here we have a C double bond O next to an NH, which is an amide. You should be able to recognize those immediately. An amine is C next to an N, but it doesn't have to have like H, it doesn't have a double bond O. C double bond O, NH is going to be an amide, right? Amine, amide. A student prepares a pure solid sample of paracetamol for 4-nitrophenol in 2 stages. So we've got 4-nitrophenol, something happens, they get an intermediate, then they add this acyl chloride, CH3COCl, and they get paracetamol. Whoop-de-doo. It says, describe a 2-stage synthesis of 5 grams paracetamol from 4-nitrophenol. The overall percentage yield of this is that. In your answer, give the mass of the 4-nitrophenol, required reagents and intermediate, and details of the purification and of paracetamol as well. So what we need to do is we need to figure out what all of these steps are first before we can really go in and say what's happening. So here, we have some mysterious intermediate, and then by adding an acyl chloride, COCl, we end up making an amide. Now, in order to make an amide with an acyl chloride, what must have been it must have been added to an amine group, right? Because the C double bond OCl, the C double bond O here came from the acyl chloride. The NH must have come from an amine bit. So what we must have in our intermediate it's got to be NH2 on this side, and then it has to have an HO, right? So then here, stage 1 must have involved, well, we're going from NO2 to NH2. We must have reduced it with SN and concentrated HCl. There you go. So we've actually done that first part here. So let's talk about the reagents and intermediate first. So reagents and intermediate. Well, the reagents are going to be SN concentrated HCl, because you can see there's NO2 and we're going to make this. And the intermediate is going to be HO, this, and then NH2. So we've done that first bit, done. So reagents, intermediate, happy. Now we need to figure out the mass of the 4-nitrophenol required and all of that jazz, right? And then also how you would actually purify it. So here, let's work out what we have. So we want to make 5 grams of this, right? From 4-nitrophenol. This question is saying you want to make 5 grams, which means that your percentage yield, once you've applied it all, is going to be 5 grams in the end, as in what you end up making is that, factoring in the losses. That means that 5 grams of the paracetamol would be 40% of the theoretical. Because remember that percentage yield equals your actual over your theoretical times 100, right? So then theoretically, the theoretical mass should be 5 divided by 0.4, or you can rearrange that, either's fine. So our theoretical mass instead is going to be 12.5 grams. Now we have the theoretical mass of this. We can now figure out eventually how much of this we'll need, because this is a 1-to-1 ratio, because nothing else is changing between these other than these groups getting mucked about. So 1-to-1, right? So what I can do is I can work out the moles of paracetamol now, using this theoretical value, which is going to be its mass, 12.5 grams, over the MR of paracetamol, which you can work out by just counting up the stuff in the diagram, which is 151, which ends up giving you 0.08278 moles, right? Now, because they're in a 1-to-1 ratio, the moles of the 4-nitrophenol would also equal to this. So then the mass of the 4-nitrophenol would just be moles times its MR, which is going to be 0.08278 times the MR of nitrophenol, which is 139. If you do that, we get 11.506 grams, or 5067, so therefore that's roughly 11.5 grams. We'll stick to the number of significant figures or decimal places they give us in the question, so that's that. Chillin'. Great. So now we've done that part. Now we need to do the details of the purification of paracetamol. So what we're doing is we're purifying a solid. When you're purifying a solid, what you want to do is you want to get rid of all the other garbage in it. If we're purifying a liquid from another liquid or separating them, then we use a separating funnel, pour off either the aqueous organic layer, or whichever one's higher or lower, right? Whichever one you want, and whatever. Here we're not doing that. what we are doing is we're going to be filtering under reduced pressure and recrystallizing it as well. So what we need to do first is we need to dissolve the solid paracetamol and the minimum amount of solvent for this. So you would dissolve the impure product, the impure paracetamol here, in a minimum amount of hot solvent. The reason being is because you want it to be soluble in this when it's hot. So it will dissolve when it's hot, but when it's cold, it's not going to dissolve anymore and it will come out as a solid, right? So then what you would do is you would then cool and filter the solid under reduced pressure. And what you would do while doing that is you're going to wash it, with cold solvents. You don't want to use the hot solvent, you're just going to redissolve it again. You want to get rid of everything else that's like rubbish, right? As you want to get rid of all of those soluble rubbish impurities. So then you would wash with cold solvent and you'd filter it. And actually, while we're here as well, with the cooling part, what you should really do as well is scratch like the glass or whatever it is you're using, so like the beaker or like the watch glass, to start crystals forming as well. So for example, like, watch glass with a glass rod. Not too hard, it's just so you can have a little bit of something for it to form on those crystals, and there you go. That's it. So the student carries out 2 experiments based on succinic acid, which is this, and then aqueous succinic acid can be neutralized by aqueous sodium hydroxide here, and this reaction can be used to determine a value for the enthalpy of neutralization, which is where 1 mole of water is produced from the neutralization of an acid and an alkali. Blah, 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 standard states, all that, right? The student follows this method, so what they do is they get 50 centimeters cubed of 0.4 mole per decimeter cubed succinic acid to a polystyrene cup. They measure out 50 centimeters cubed of 1 mole decimeter cubed NaOH, which is an excess, and they measure the temperature of both solutions, add the NaOH to the aqueous succinic acid, stir the mixture, and then record the maximum temperature. And here's their temperature readings, fine, and it says calculate the value for the enthalpy change of neutralization in kilojoules per mole. And then it says assume that the density of all these solutions is the same for the specific heat capacity of water. So what we need to do is we need to figure out the energy change first by using Q equals mc delta T. Right, M is the mass of the thing which is experiencing the temperature change, as in not the mass of the substance, it's what's being either heated or cooled depending on whether it's losing or gaining energy, which is going to be the volumes of these 2 solutions, which is going to be 50 plus 50, right? And we're assuming that it's got the same density as water as well. So 1 gram of water has the volume 1 centimeter cubed. So 1 centimeter cubed, 1 gram, right? That's its density at room temperature, pressure, blah, blah, blah. So that means if we have 100 centimeters cubed of this solution, we're going to have 100 grams as the mass. C is going to be 4.18, and delta T is going to be our temperature change, which is going to be 5, right? 5. So then that's Q. Remember, Q is measured in joules and it's an energy change. So Q equals 100 times 4.18 times the temperature change, delta T, so 5, which is 2090 joules, which if you convert that to kilojoules is 2.09 kilojoules. However, the units here says kilojoules per mole, meaning 1 mole of whatever will give this energy change of that, right? Here we only have kilojoules because it's only the energy change. We don't know how many moles made that energy change. The reason we do per mole is because we want to make it consistent, and that's why all the definitions say 1 mole, right? We want to make sure that we have 1 mole, because if I have 2 moles, it would double the amount of energy change happening. So we don't know how many moles produce this energy change yet. So we need to figure that part out. Now, this is the enthalpy of neutralization for succinic acid. The whole point of the experiment is to work out the enthalpy of change of neutralization for succinic acid, right? So we need to figure out how many moles of succinic acid led to that energy change. So the moles of the succinic acid is going to be its concentration times the volume we used. So the concentration in the question was 0.4, and the volume, not at the end, the moles that we added, because if you use the volume at the end, you're going to have a higher volume, and it's going to look like a higher number of moles. We're not doing that. So it's going to be 50 over 1,000, which ends up giving you 0.02 moles. Therefore, 0.02 moles caused this energy change, 2.09 kilojoules, right? So then 1 mole would give you 2.09 over 0.02, which is going to be 104.5 kilojoules per mole, right? Now that's going to be exothermic because heat was released, the energy change, the heat went up, so it's going to be minus 104.5 kilojoules per mole, but we're not done because it's asking you the enthalpy change of neutralization, which is where 1 mole of water is produced, right? Here there are 2 moles, so this is double what it should be. So that's why I was saying the definition before, because it's important to know your definitions. So the actual value of this is actually this times a half, which ends up being minus 52.3, because they want the enthalpy of neutralization of this. This is only going to tell you the enthalpy change of what this reaction is for every mole of that. That's all. We want to make it the neutralization enthalpy change, which means it has to be 1 mole of water produced. Succinic acid is esterified by ethanol in the presence of an acid catalyst to form an equilibrium mixture. This equilibrium constant can be calculated using the amounts of moles in this equilibrium mixture using this expression. A student carries out an experiment to determine Kc. They mix this much of succinic acid, this much ethanol, and then they allow it to reach equilibrium, and then they determine that 0.02 moles of succinic acid are present in this equilibrium mixture. So what technique could they use to figure out how many moles of this this stuff there is. So you need to find the moles of some mysterious thing, right? We can do that using the moles of something else, because we'll know what that something else is. So it's titration. Titration, the entire point is finding out the concentration, moles, or volume of some other mysterious thing using a known amount. Then it says write the equation for the equilibrium reaction that takes place, right? Here it tells you what's up. These are your reactants, those are your products. So therefore it's going to be CH2COOH2 plus, whoops, it's that, C2H5OH, but squared, there's two of them, gives you CH2COOC2H52 plus, and then 2H2O. That's it. So then it says, draw the skeletal formula of the ester produced. I would start with like the double bond O bit, because that's what came from the acid, right? I think esters are something people are unnecessarily scared of, in my complete opinion, because the key link here you need to know is that there's a C double bond O and an O and then this, right? This part came from the acid, that part will have come from the alcohol. So we were told that we're using succinic acid, which in the question told you is butane dioic acid, right? So that's going to be 1, 2, 3. So 1, 2, 3, 4, double bond O, HO, double bond O, OH, right? And we've reacted it with 2 lots of alcohol. So we're going to have 2 ester links formed. So what I usually do is start by drawing the ester part, and the rest falls into place. So you're going to have double bond O, right? Actually, I can make this look a bit tidier. We'll have the double bond O bit here, and an O, and then the rest of this will be the alcohol, which is C2H5. So there's your the C2H5e bit that went. Then I got to draw the bends for the butane. So 1, 2, 3. So that's going to be 1, 2, 3, 4, and then here we have another ester link that would form as well, because we have 2 alcohols in this as well. They've given it to you in that question. So here we'd have a double bond O, we'd have an O here, and then another bend like that. There you go. That's it, done. So then it says Kc is the equilibrium constant in terms of equilibrium concentrations. Why can this expression be used? And the question told you that they were able to use the moles of it. The only reason that they were able to use moles must be that the volumes have cancelled out. There you go. So now it says calculate the value of Kc and then show your working. So in order to work out Kc, they've told you in the question that we can use the moles. So I'm going to quickly sketch out what that reaction was again. So it's going to be the succinic acid plus the ethanol, right? The 2 ethanols gives you 1 ester and 2 waters, right? Initial moles, final moles, or equilibrium moles, really. The question says they mix together this much of the succinic acid and this much ethanol, so 0.05 succinic acid moles, and then 0.150 moles of ethanol. And then in the equilibrium, it says that this much was present in the equilibrium mixture. So before we have an equilibrium, there's 0 of this and 0 of this, right? But then in the equilibrium mixture, they said that this much succinic acid was left, so 0.02. This has fallen then by minus 0.03. This must have gone down by 2 lots of that, because every one of these needs 2 of them to react. So that will go down by 0.06. This must have gone up by, well, there's 1 of these and there's 1 of them, so it must have gone up by 0.03, and then there's 2, every one of these makes 2 of them, so that will have gone up by 0.06. So therefore, the equilibrium moles of all of this stuff is 0.02, which you've got. This will be 0.09. This will have gone up by 3, so 0.03, and then that will be 0.06. Now, in the question, they've told you can just use the moles straight up, because volumes all cancel out from what we've said before. So then all you do is just plug them in. So Kc will equal this ester, so 0.03 times the H2O, but there's 2 of them, so it's going to be 0.06 squared, all over the 0.02, the succinic acid, times the 0.09, which is the ethanol, and that's squared as well. If you do that, you end up getting 0.667. So you should follow the same number of significant figures or decimal places in the question. I'm actually going to go with 0.67 because there's 2, so there you go. Okay, so this question is about organic reactions. Compound A is formed when ethanol is mixed with OH minus ions, which acts as a catalyst. What do we have then? So here, 1, 2, 3, 4, right? So it's 4 carbons. So it's going to be butan. It's an aldehyde, so al. And there's 1, 2, 3, so it's 3 hydroxy. Now it says, what type of reactions happened? Well, can you see how this is this? And then now it's this. We've added on an extra, bit to this. We've added a C with an OH on, so it's going to be addition. It's not substitution and it's not elimination. There you go. Now it says this reaction takes place in 2 steps. OH minus acts as a catalyst. In step 1, ethanol reacts with OH minus to form an acid-base equilibrium, and then in step 2, compound A is formed. Complete the equilibrium for step 1 and then label the conjugate acid-base pairs as shown. So any acid in the universe can lose an H+, any base in the world can gain the H+, right? So whichever one's losing and gaining. Here, this isn't going to really lose. I mean, it allows it, but realistically, come on, that's your base, right? We always know that to be a base. So if that's acting as a base, right, B1, then there's got to be an acid after which it's gained a proton. So if it gains a proton, you'll end up making H2O like that, right? It's gained an H+. So that means that's your acid 1. This must have gotten that H+ from somewhere, right? So this means this has to be an acid. Because this is an acid, it must have lost an H. So then it could be, CH2 minus CHO, or it could be CH3CO minus. But can you see how this has lost an H plus to get there? So that's your acid 2. This can gain an H plus to get back there. So that's your base 2. Conjugate acid base pairs. That's all it is. Since I suggest an equation for step 2. So in step 2, compound A is formed. We end up making this mysterious thing here. And they've told you that in step 1, we react to this ethanol with OH minus to get an acid-base equilibrium. So we're going to end up using one of these, right, as our second step because it's not there in the end. So CH2CHO minus plus something ends up making this thing here with an extra whole ass carbon in it, right? And we don't have any H2Os in here. We don't have any other stuff. So what we are adding most likely is we're going to add an H2O in this, definitely, because it needs to go. We don't have this anymore, and we end up making that final product, which is CH3, CHO, CHOH, CH2, CHO. And this is a catalyst, remember? So we have to remake that OH minus again, right? So if you have a look here, 2 carbons, but now we have 1, 2, 3, 4, right? And the only things, we can't add any magic new things in here. So what must have come into this is probably another one of like these. As well, it's shown you that we're using 2 of them as well. So it could be that there's just another one of them in there. So one of them reacted in this step. The other one from, here, because there's 2 of them of the equation above, must have reacted in the second step. CH3, CHO, plus that. Because then you've got 2 of them, which is in the overall equation. None of these, because there's none in the overall equation, right? Whoops. And then as well as that, you've now made this, and then OH minus is a catalyst, it's reformed. There you go. So similar reaction takes place when propanone is mixed with OH minus ions, give a structure for the product of this. So if you have a look here, we have a C double bond OH, right? That stayed the same here. But what's now happened is we've inserted a CH2 and then a CHOH, right? That CHOH must have come from here, which is a C double bond OH. So that must have turned into a OH, and that's where this piece has come in. So what we've done is we've added a CH2 and then this thing, but with an OH instead of an O, double bond O, sorry. So it'll be the same thing here. What we'll end up having is we'll have this C double bond O here that's the same as this CH3. We'll have added in a CH like this, and then we will have added this whole thing again, but that's an OH instead. So COH, CH3, H3C like this. So that's what you end up making. So now it says many organic compounds use electrophiles as reagents. Explain the role of electrophiles. Your answer should include one reaction of an aliphatic compound and one with an aromatic compound, including a relevant mechanism. So let's talk about what an actual, electrophile is. So an electrophile is an electron pair acceptor, right? And the 2 types of mechanism that you're going to use, well, if it's aliphatic, the only one that you know is electrophilic addition with alkenes, and aromatic is electrophilic substitution with benzene. Let's do the aliphatic one first. So aliphatic, you're going to do the electrophilic addition of alkenes with I'm going to do HBr, or something like that. The reason I'm doing that is because then I can get extra points to talk about the major and minor product stuff as well. With HBr to form haloalkanes, right? So then what I'll do is I will just pick something that does that. We can do the other one as well, but you'll get extra marks for like saying every possible detail. So I'm trying to squeeze everything out. So what I'll do is I'll draw the mechanism. So I'll have C here, for example, and then CH3, CH3, H, and H. So I want to make it crystal clear that that's going to be the major, right? So in this electrophilic addition model, electrophilic addition, what we have is we have the electrophile. So we have H, Br, chilling here, right? Now remember that this repels the electrons here. So we already have a dipole because this is more electronegative, so it's pushing them there. But because it's floating around here, it's polarizing it even more. So as a result, what happens is you get a delta minus here and a delta plus here. This will then donate electrons to this, and there's too many bonds on here now, so it's like I need to boot something off. Again, you can't boot something off without showing the direction the electrons are moving, so what happens is the electrons go like this. So what you end up making is you'll end up making CC, CH3, CH3, and a carbocation here, H, 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 and your Br minus will go here, right? Or you could end up making CC, CH3, CH3, H, and then carbocation here as well, here and here, like that, sorry. Then your Br minus instead would go here, right? And then what you would end up making are your 2 products. You end up making your products, it's going to be CH3, 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 and then a Br here, and then you would have a C, H, H, Br, C, CH3, A, CH3. That's going to be, and we should explain this is your major product, that's going to be your minor. The reason is you get that major product forms because that carbocation is more stable due to more alkyl groups. I've rinsed every possible thing I can say about electrophilic addition right there, done and dusted, finessed, right? So that's that one. The next one is electrophilic substitution, right? So in electrophilic substitution, you can choose whichever one you want to use as an example. Choose any example you want. It's probably easiest to stick to a nice one, like, NO2, nitration of benzene. So e.g., the nitration of benzene, and that's electrophilic substitution. So this one's a bit different because we need to first of all generate the electrophile. So what you end up having is you'll have HNO3 plus H2SO4 makes NO2 plus HSO4 minus plus H2O, right? Then what will happen is you draw the actual mechanism. So you end up having your benzene ring happy days like this. Your NO2 plus will form a bond with it. You need to show which way the arrows go. Because you're making a bond and it's an electrophile and it likes those electrons, it will do this. Then what you'll end up with is you'll end up with this intermediate where the benzene is now broken. So you'll have this NO2 here happy, but this is now broken and we want to fix that. So we need to, this carbon also has too many bonds for benzene. Although lots of them like having 4 in benzene, they have 3. So we need to break this bond. So you wouldn't draw the arrows going this way because that'd make H minus and 2 plus here. We want to fix this, so we're going to put the electrons going in like that. Then what happens is you'll end up making your nice benzene ring again, NO2, and an H plus. So then what happens is you regenerate the catalyst. So what happens is you'll have HSO4 minus plus H plus gives you H2SO4. There you go. And that's it. There you go. Thank you very much. I hope that helps. Please like, share, and subscribe, and you know the drill. As long as you follow things systematically and step by step and really use what the question's telling you, a lot of this gets a lot less evil. Anyways, thank you. Bye-bye.